Okay, so let's assume now that the force of gravity changes with time, that it increases. So instead of minus mg, we'll multiply by some other term that has a time. So we're dividing by a constant c. That's also a time, so that it still remains a force, and it's still in the vertical direction, in the minus y direction. But it's a time-dependent force, so we'll now look and see what happens to the work. So the work is still, again, because it depends on time, we want to go through endpoints in time. So we're going to have minus mg t over c j hat dot, well, let's, we have to write the dy in terms of time. So what does this look like? Well, a y from this, right, we're doing f equals ma, so we're doing minus g t over c for the acceleration. And so the velocity component, where we're integrating that, we have a constant of integration. If we launch an object upwards, initially with speed v naught, minus gt squared over 2c. And then we have y equals y naught plus v naught t minus g t cubed over 6c. And so, of course, the dy will be v naught dt. It's a little bit different compared to before because we have gt squared over 2c in dt. And so the work looks like minus mg over c. That can be pulled out from t1 to t2. There's a t part of this that stays there. We've done the dot product, j hat dot j hat is 1, and so the dy now goes here in terms of time, minus g t squared over 2c dt. We integrate that, we get minus mg over c times v naught t squared over 2 minus g t to the fourth over 8c evaluated from t1 to t2. This is minus mg over c, v naught over 2, t2 squared minus t1 squared. Again, we'll make t1 0 plus mg squared over 8c squared, t2 to the fourth minus t1 to the fourth, and t1, as we said, is 0. T2 is given by, we're coming to here, and we want to come back to the same point, so y minus y naught is 0, so we have 0 is equal to v naught t2 minus g t2 cubed over 6c, and that gives us that t2 is equal to the square root of 6c v naught over g. And so the work is minus mg v naught over 2c times 6c v naught over g plus mg squared over 8c squared times, we're going to square this, so 36c squared v naught squared goes to the fourth over g squared, and that is minus 3 m v naught squared plus 9 over 2 m v naught squared, and that is 3 halves m V naught squared, if I did that right. But that's also equal to the difference in kinetic energy, which is K final minus K initial, which is K final minus, if we launch the object up with speed V naught, looks like that. And so K final, when the object comes back to the same height, that is equal to m V naught squared over 2 plus 3 m V naught squared over 2, which is 2m V naught squared. And so we see that the object has come back to the same height, so its potential energy is the same, but it has a different kinetic energy, and so E, the energy, is not conserved. So the force needs to be not a function of time. That's crucial. It's a crucial feature of energy conservation, and it also needs to be possible to write as a gradient of a scalar function. So friction, for example, would not work like this, and so we need both of these characteristics, but time independence is crucial for energy conservation.